Welcome back everyone, Mr. Allen here. Just going to lead you through kind of sketching logarithms here. Before we can do that, we need to sort of understand where logarithms come from. So I've got the equation f at x equals 2 to the x on my graph. We should remember from before that 2 to the x is basically just taking obviously the different x values here and putting them into the equation that's given, so that we're finding 2 to the exponent 2, 2 to the exponent 4, and so on. As we go back here, we're getting numbers like 2 to the exponent negative 3, 2 to the exponent negative 10,000. And just to sort of make sure everybody recognizes and realizes, 2 to the exponent negative 10,000 is 1 over 2 to the 10,000. And from what we've seen before, that will never be 0. Anytime we have a fraction or a rational expression with a number on top other than 0, we can't get 0. And so in this we have a horizontal asymptote. So moving to the log then. The log is the inverse of the original. So if we kind of look at just a few key points here, the point 2 to the 4 up here, and the point 2 to the 4, 2 comma 4, it came from 2 to the 4 in the original expression. 4 comma 2 then is on my log. Here I have 0, 1, here I have 1, 0, and just kind of a couple more. 0.5, negative 1, and negative 1, 0.5. So you can see that basically the log curve, essentially all the y values from our original, from our exponential, are now the x values from the log curve, and vice versa. And so that's why I kind of wrote this way. The y values here were the x values that were used here. So that should suggest then that if we had a horizontal asymptote with our original, we now have a vertical asymptote with the logarithm. So I'm going to take the exponential off here, hide these points. Now the other thing to sort of understand with the with the logarithmic curve here, there are two key points that will always be in our base curve. The first one is the point 1, 0. So sort of if we think about what we had originally, we had some number to an exponent. If that exponent is 0, regardless of what the base is, so 1 to the exponent 0, 7 to the exponent 0, 23 to the exponent 0, the answer is always 1. Because again the logarithm is now that concept reversed, the exponent itself, the exponent that we were using, the 0, is now the answer to our expression. It's now the y value in our expression. The point 1, 0 will be crossed by every regular logarithmic curve. So along with the point 1, 0, again, which will always be on every curve, a second key point can be found by going to the base number to the on the x-axis. So as I go across, base is 2, looking at x2, I get the point 2, 1. If I had a different base on my exponent here, a 4, at the x value 4, the value will be, the point value on the curve will be 4, 1. And continuing, of course, base of 7, across to 7, 7, 1. So the question then is, how does that help us with transformations? And so if I look at a little example here, the base log function, when we don't have a base indicated here, is indicating that we've got a base of 10 by default. And so what we know is that our logarithm in its normal form, the log x specifically, will have an asymptote first of all here to begin, and it will have two key points. Those key points would be the point 1, 0, And then again, if the base is 10, the point, say, 10, 1 would be our second key point. So 1, 0, and 10, 1 would be our sort of key points, and our curve would do something like this. Now in this case, we want to shift based on this parameter here, and this parameter here we've seen before is going to move us to the right. So this is a horizontal shift, and of course the shift is opposite to this because it's the value that needs to be plugged in for x. So we want to shift right. So the 2 points in our normal function, sorry, messed that up, are 1, 0, and 10, 1. They need to shift 1 to the right, which means they will now be 2, 0, and 11, 1. And so instead of this, I'm going to be cutting here. Instead of the 10, 1, I'm out here at 11, 1. And then if the entire graph is shifting to the right, that means the asymptote itself is shifting as well. And again, 1 to the right. And so now my graph is this one. And that's really all we're going to be doing for now for sketching transformations of logarithms. Sort of taking the 2 key points, shifting them according to whatever information we have, and then basically recognizing where the asymptote shifts as well, and sketching it in like that. So looking at the second one here, my base function is log base 2, and so my 2 key points are 1, 0, and 2, 1. And this tells me I need to move to the left 5, and this tells me I need to stretch vertically 3. And so basically I'm moving this value to the left 5. So from 1 it's got to go back 5 to negative 4. Whoops. The 0, the vertical, the y value has to stretch by a factor of 3. Of course 3 times 0 is just 0. Over here my 2 is going to shift to the left 5, so it will be at negative 3 now. And my y value is going to be stretched vertically. It's going to be a 3. The entire graph has shifted, we said 5 to the left, so my asymptote will be back at negative 5. And so this is x equals negative 5. My 2 key points are negative 4, 0, and negative 3, 3. And now my sketch will look like this. Okay, so again, logarithms will be one of our simplest things to sketch transformations with. The basic shape never really changes. It stretches again, of course, vertically, horizontally, depending on the parameters that we have. The key will be that the base establishes where our second key point is, and then basically get in the asymptote, get in the 2 key points, and draw the line through, knowing that we go sharp vertical, and then as we hit that second point we flatten out considerably. Just one last note, I guess. With all of these, our domain will always be the values to the right of the asymptote. So in this case my domain is x is greater than negative 5. And although it looks like this flattens out considerably, it does continue to go up. And so my range for all of these will be y is just any real number.